Have you ever really thought about how we manage to tame a massive raging river so that it can reliably feed something as simple as an irrigation canal? It's one of the oldest and coolest challenges in civil engineering, and the answer is this incredible collection of structures we call canal headworks. So today, we're going to break down exactly what they are, how all the pieces work together, and of course, why they sometimes fail. Okay, so let's get right into it. A diversion headwork at its heart really just does two main things. First, it puts a big obstacle across the river to jack up the water level. And second, it uses that new higher water level to gently push a controlled, predictable amount of water into a canal. It's all about turning a wild, unpredictable river into a steady, reliable water source. Simple as that. Now, what's so great about this slide is that it gives us the bird's eye view of the whole operation. You can see the main structure spanning the river, you see the canal taken off from the side, and then all these other walls and channels supporting it. Before we get into the nitty-gritty, this is what the entire system looks like. We're going to dissect this piece by piece. So here's our game plan for this explainer. We're going to start with the main event, the structure that actually controls the river. Then we'll look at how we guide the water, and crucially, how we manage all the silt. After that, we'll check out the canal's entrance itself, and we'll finish up by looking at the powerful forces that can actually cause these huge structures to fail. All right, so the very first big decision an engineer has to make is how exactly are you going to raise that water level? And this brings us to a classic comparison you will see on pretty much every single civil engineering exam, the choice between building a weir or a barrage. And this slide right here nails the fundamental difference. A weir is basically a low, solid dam. It gets the job done, but it's kind of a blunt instrument. A barrage, on the other hand, isn't solid at all. It's a series of massive, adjustable gates. It gives you so much more finesse and a way higher degree of control over the water level and the flow. So if you're studying for an exam, here's the magic number you need to remember. It's a great rule of thumb. If you need to raise the water level more than about 1.5 meters, the limited control you get from a weir just isn't going to cut it. You need the flexibility that a barrage provides to manage that big of a height difference. And this is exactly why barrages are seen as the more modern, more advanced solution. Think about a flood. You can just open the gates wide and let the water rip through with minimal obstruction. That means less afflux, which is just that backup of water upstream. You get better control over flow, which means you have way better control over silt, and hey, you basically get a free bridge out of the deal too. Now, that's not to say weirs are totally obsolete. Modern concrete weirs, like the one you see here, have this cool sloped floor on the downstream side. It's called a glacis. That slope is precisely engineered to create something called a hydraulic jump. It's this zone of really turbulent water that safely burns off the enormous energy of the water falling over the top, so it doesn't tear up the riverbed downstream. Okay, so we've raised the water. Awesome. But that's just step one. Now you have to very carefully guide that water toward your canal, and at the same time, you have to deal with a river's biggest headache, all that sediment and silt it's carrying. Let me introduce you to the unsung hero of the whole system, the divide wall. This thing acts like a giant barrier, and it separates the wild, turbulent flow of the main river from the area right in front of where the canal starts. This creates a nice, calm pocket of water, which is absolutely critical because it allows all the heavy silt to settle out before it has a chance to get into the canal. So what happens to all that silt that settles down in that quiet pocket? Well, that's where the undersluices come in. You can think of these as the cleaning crew. They're just low-level gates right next to the divide wall that you can open up every so often to create a powerful flush that scours all that built-up sediment and sends it downstream, keeping the entrance to the canal nice and clear. Of course, we can't just block off the entire river. We have to think about the fish. A headwork structure is a complete barrier to fish migration. So to solve this, we build a fish ladder. As you can see, it's basically a sloped channel with these baffle walls that create a series of small, calm pools. This lets fish swim and jump their way upstream, safely getting past the big obstruction. Okay, we've raised the water, we've made a nice, clean approach. Now we're at the very front door of the canal system itself, the head regulator. This thing is the final gatekeeper that decides exactly what and how much gets into our irrigation network. The head regulator really has three big jobs. Job number one, its gates control the amount of water we let into the canal. Job two, it can be slammed shut to stop a river flood from destroying the entire canal system. And job three, its floor is raised up a bit, which helps it skim the cleaner water from the top of the river, leaving that nasty, silt-heavy water at the bottom behind. Now, you can run this whole system in one of two ways. You've got still pond regulation, where you keep the undersluices closed to let the most silt possible settle out. The catch is you have to shut down the canal for a day or so to flush it all out. Or you can do semi-open flow, where you keep the sluices just a little bit open all the time. This creates a constant, gentle cleaning flow, which means the canal can run continuously. This leads us to two really advanced silt control devices that are super important. And let me tell you, they are a classic source of confusion on civil engineering exams. So you're going to want to pay close attention to the key difference between these two. So here it is. The one crucial thing you need to remember is location, location, location. A silt excluder is built in the river before the canal entrance. Think of it like a bouncer at the club door, stopping the big, coarse sediment from ever getting inside. A silt ejector is built inside the canal itself, a little ways downstream. This is the device that kicks out the unwanted guests who already slipped past the bouncer. Okay, finally, to really truly understand these massive structures, you have to appreciate the incredible forces that are constantly trying to tear them apart. Understanding how they fail is the absolute key to designing them right. And failures really fall into two main categories: what happens under the surface and what happens on top of it. First up is piping. This is the silent killer. See, water always wants to seep underneath the structure. If that seeping water moves fast enough as it comes out on the downstream side, it can start carrying tiny soil particles with it. That process slowly carves a hollow pipe backwards under the foundation until suddenly the whole thing just collapses into the empty space. And then you have scour. If piping is the silent, sneaky killer, scour is the violent, brute force attack. This is simply the raw power of the river's current, especially during a big flood, just digging away at the riverbed right next to the structure. If it digs deep enough, it can completely undermine the foundations, causing the structure to literally topple over. And here, you can see how we fight back with engineering. To stop piping, we drive deep walls called sheet piles into the ground and build a really long concrete floor to make this seepage path for water super long and slow. To stop scour, those same deep piles act as a strong foundation, and we lay down protective blankets of rock. Every single element is designed to counteract these immense forces. Which leaves us with one final and pretty big thought. All of these designs were based on river data from the past, but as climate change gives us more intense floods and totally unpredictable river flows, how are engineers going to have to adapt these fundamental structures to make sure they can still stand strong and continue to provide the water we all depend on?